This is a question I really like. Actually, the time that I first read this one, it was the same time period where I was reading the one about the jet planes and talking about how to fit people in the cockpit, and that there was a knee restriction, distance between people's knees and the handles and so on, or the componentry. And I liked it because I had a lot of friends that were pilots at the time, and I guess I still know a few. But anyway, it's an interesting question. A survey found that women's heights are normally distributed with a mean of 62.9 and a standard deviation of 2.6 inches. The survey also found that men's heights are normally distributed with a mean of 67.4 inches and a standard deviation of 2.6. That's interesting. They have the same standard deviation. Anyways, coincidental. Complete parts A through C below. Most of the live characters at an amusement park have a height requirement with a minimum of 4 feet 9 inches, right? And a maximum of 6 feet 2 inches. Find the percentage of women meeting the height requirement. How are we going to do that? Well, we've got the distribution that we can create based off of that. It's really just the same thing as what we're talking about in other times, adjusting the standard normal distribution. So here's the standard normal distribution, or at least the table for it, I should say. And what we want to do is adjust it so that way we can look at the z-scores. But we don't actually have to do that manually because we have technology, the StatCrunch tool, the TI-83, Excel, StatDisk, and so on. Let me get you the PowerPoint sheet really fast to show you this. This is our chapter where we first started talking about continuous distributions, and we started with the normal distribution and explained that it's essentially this density curve that can be defined by this, but this function is based off of these z-scores. In other words, the expected means and the data points shifting their deviations from the expected mean divided by the deviation, standard deviation, and so on. So anyway, without getting too much back into that, sorry, we learned that we wanted to start looking for the area underneath this curve because it corresponds to the probability of an event occurring that's described by the curve. And the standard normal distribution is the one that uses the z-scores, right? And that the table's made out of. But what we want to do is change those boundaries from z to just a non-standard normal distribution. So it's still normal distribution, but it's non-standard. And so we reach back to chapter 3 to find the conversion between standard deviation and any old data point in our set, and that was this, that z equals the deviation x minus, and back then it was x minus x bar because we were using observed data and not the expected data, mu. But it's the same concept in words, same concept and the same words. It's the data point minus the mean divided by the standard deviation. Except for back then that used to be an s. Okay, and we're going to convert between a non-standard and a standard, and then we can look up things on the table, and then we can go right back. So in another video I demonstrated that you can imagine taking this thing right here and turning it over, but then you'd have to use algebra to multiply by the standard deviation and add the mu, or add the mean. Alright, so consider the flowchart that was in the book, and they also have a good flowchart animation for. If you're not checking out the flowchart animations in the Tools for Success, or just as they appear in the homework off to the right under animations, you're missing a great opportunity to solidify some learning. Either way, here is what it says. It says, this flowchart, what do you want to find? Do you want to find the probability, or do you want to find the value x given a certain amount of probability? Well, let's go back to our question to decide. Since our question is saying to find the percentage of women who meet this height requirement, then we clearly want to find the percentage. So let's get over here. We want to find the probability. Okay, are you using technology? Sure, we'll use technology if that's the case. We can find the probability using technology. If we weren't, we could use the conversion, go to the table, and so on. So I'm going to use StatCrunch since that now has this great ability to find in-between values. And that is what we need for this problem. is in between 4 feet 9 inches and 6 feet 2 inches. If I had that right, let me just double check. Right. Okay. And so again, make sure that we're talking about the right distribution. This is women, okay, and women's heights. So we're going to use a distribution from the women's heights. Choose stat, pick calculator, choose the normal calculator. Let me get this up here on the screen a little bit. You know what? It's not going to let me show you everything. So we'll just remember it's 4 feet 9 and 6 feet 2. Now if you're doing the table, it's a little bit of a mess because you have to go find in the table the left area up to one endpoint, the furthest right endpoint, and then find the left area up to the left to the furthest left, and then you subtract that area off and you're left with the in-between. StatCrunch now, StatDisk, the TI-83 can all do the in-between as part of a function. I don't know if Excel can. I haven't done Excel in a long time for this because I went to the calculator when I found out that worked, and I stopped using anything else except for the calculator until I found that this worked, that they made this feature available. 62.9. Okay, so what I'm going to draw now will be a non-standard distribution. And we wanted to go from, it's really nice when we don't have to do all the conversion. We need this in inches, so 4 times 12 is 48. We're going to add 9 to that. So we'll put here 48 plus 9, 57. And 6 times 12, 72, plus 2, 74. And you'll notice that it says an x value. It was saying x even though I previously had in 0 and 1 and it thought it was a z distribution, a standard normal distribution. But it's really good that it has the x here, because what we're saying is what's the probability of finding a data value, okay, picking a woman, that falls in between the heights here, 57 inches and 74 inches, based on this distribution of women's heights. And it says 98, if I move the decimal over 2, right? 98 and 83/100%. Let's see why they, I'm sorry, rounding 84. So that's why they gave us as a right answer 98 and 84/100. All right. Okay, then the next one, find the percentage of men meeting this height requirement. Now make sure you're using the right mean. The standard deviation coincidentally was the same on this, so that wouldn't have messed us up, but if we use the wrong mean, it's not going to work. And it's very easy to just switch that to 67.4, and we're using, even though the original question was about women, we're using the same height requirements, because they didn't imply that we were changing anything, right? We were just talking about men. I mean, that's the only thing we are changing. So don't change any of those. And there we have 99.44. What's that telling you about men? It's telling you that men on average are taller, right? And so you're going to fit more of them in that range. But they're not so much taller that they're taller than 6'2", although there are men and women taller than that. So 99.44. Okay, if the height requirements are changed to exclude the tallest 5% of men and the shortest 5% of women, what are the new height requirements? Great question. Very interesting, right? So we've got to bounce between the two distributions, and here's what we're going to do. I want to show you both distributions, and I'm going to take a little bit more control, active control of it. Here's a file that I made called normal distribution. The extension GGB stands for GeoGebra, and it's a free program. In fact, I'll just click on this really fast. GeoGebra. This is 4.2.6. You should look it up, anyone, because it's free. The guy who created it, it's just awesome. Marcus, had a couple encounters with him, and he did it as a master's project, a joint master's project. He did a computer science master's and a math master's, and this was his result. And he's developed a community behind it and got people to develop for it, and it's just a cool tool. All right, that's long enough about that. So let's get this distribution in here. We want this distribution to have the mean of, I'm going to go with the men's first, since that's just the way it was worded. The height requirements changed to exclude the tallest men first. So we want 67.4 and 2.6. I'll quickly double click on this scroll, or on this slider bar, choose the slider range, and I'm going to let it go all the way up to 67.4. I'm using increments of 1/10, and that will let me to I'll slide all the way down the end. Okay, now you notice that my curve just disappeared. It's because it slid down there, away from the standard distribution. And then this needs to be 2.6. What's cool about that is once I set this, I can use it for both. Yeah, let me drag this over here. Now, you'll notice the curve also looks different in terms of its height. That's because if its normal standard deviation for the standard one is 1, and we've changed it to 2.6, the standard deviations have become longer, wider, and so this curve has gotten wider. Now we can adjust it by going back to the vertical scale and just changing the scale so it looks different. But why not just leave it like it is? It gives us perspective. All right, now we want this to pull over here. So this gives us the area under the curve from -2 to 73. I don't think we have to go that extreme. I'll come up to, well, I might as well just leave it there. Go as negative as I want, because what I'm trying to do is cut off the top 5%, right? So I'm going to exclude the 5% tallest people. And right here, I see what area is covered. Again, I'll scoot this over to be even more extreme. I have 98% covered, right? Let me scoot it over so that it's just 95 if I can do that. Now since my increments are not that precise, oh they are, I'm just going to move it with my cursor. Okay, here we're getting closer. We are going to cover, ooh, that's really close. We're going to cover 95 and 1/100%. What's that cutoff value? 71.68. Do you see that? So that means that's the height that we're going to need to be at. Okay, now let me open up another copy of this file, and we'll put them side by side. I'll adjust our mean and standard deviation from standard to non-standard. And remember, this time we want to exclude the shortest 5%. I'm going to go ridiculously high on the left side, and on the, the right side. And on the left side, I'm going to come up to the point where I'm allowing only 5% of area not to be covered on the left, and then the rest will be on the right. Go a little bit faster here. Okay, that is really close. Here are the two displayed together. Let me adjust. So we can see both the women's distribution. See, the mean is 62.9, standard deviation 2.6, excluding the bottom 5%. And the area is contained up here, and we get a cutoff score of 58.62 inches. And the men's distribution, see the mean is 67.4 and standard deviation 2.6, cutting off the top 5% there, and the height is 71.68. So let's check both of those. Rounding gave us exactly the right answer. And you could have used StatCrunch also.